Hey, John here. Let's look at the state machine that I use to implement the timing and the control and the graphic output. I mean, this is the end of the line, right? For graphic modes 1 and 2 and the text mode on the TI 99 VDP. As always, a big thanks to everybody supporting the channel, all the people that like and subscribe. Thank you very much, especially the Patreons and the VIP Patreons listed here. Thank you very much. All right, so a super duper quick recap here. I'm going to focus in graphics mode 1. I'll point out the differences between graphics modes 1 and 2 when we look at the state machine, as well as a little bit about the text mode, because the text mode has a little bit different timing because as you might recall, the text mode has a 8-row by 6-column tile. I call these things on here tiles. They call them pattern positions. Nowadays, I don't think anybody would call these things patterns and positions anymore. This thing was invented before a lot of these names were even, decided what the common words with these going to be. So as I speak today, and as the code and the variable names you'll see today refer to these thingies on the screen in here, and what is in the active display region here, that is between the left and right border, below the top and above the bottom border. These squares in here, or I guess perhaps better call them rectangles, because text mode, they're not square, right? I'm going to call these things tiles, okay? So as this diagram shows, and I assume that you've already seen this, you can take a look at the variation between graphics modes 1 and 2 on your own time. Short of that is the way you use the value from the name table to determine the offset address in the pattern table is different when you're in graphics mode 2. The same thing with the color. So the math that takes place in here is the only difference. And we'll actually see that in the code when we're going through the implementation. We've got 32 tiles by 24 tiles in here for a total of 768, because the first one is called 0. All right. So keep this handy so that you can reference it. You might have to pause this video a few times. Now, when I first planned out how to do all this, I started with a diagram like this. This one I updated just before we recorded this today to what I'll call the as-built diagram. This one actually reflects what the state machine does today. Let's look at this for a minute before we dive too much into what's going on. For each one of these tiles that we're going to render, that we were just looking at a second ago, it has 8 columns in graphics mode 1 and 6 columns when we're in text mode. And they also have 8 columns in graphics mode 2, okay? So what I've done here is I said, look, let's look at graphics mode 1. What do I got to do in here? This will also work for graphics mode 2, by the way. In other words, it has 8 columns. And you can see because I got these like 8 colors down here. So what I'm doing is I'm looking at one row of one tile being rendered in the course of time, okay? This, I added a little note here to myself to make sure that I point out this is the VGA pixel clock running up here. Recall that the VDP pixels are twice as wide as the VGA ones. So when you look at this clock here, you'll notice that this down here, the color output register, spoiler alert, this is the color of one of the pixels that's coming out of the VDP logic. So it's smeared across 2 VGA pixels horizontally, all right? So everything down here is running half the speed. As you'll see, this thingy here represents, which phase, 1, 2, 4, 8, 10, 20, 40, 80. This is a ring counter that's just shifting left all the time, okay? And each one of these periods represents one VDP pixel period up here. And you'll see that they also align with the things that are going on down here, especially where we set the color output values down here to what they're supposed to be for the period of time that they need to be. Okay, so from a big picture, notice this thing has kind of got this angle going on here. Now, this is a pipeline. So what happens is it's all driven from the VGA sync module I talked about on my channel before. And that module generates things like the VGA column number, the VGA row number, and it generates signals that says this is a good time to be showing the border color, this is the period of time on the horizontal rows, anyway, where we've got an active display region, and then you've got another border on the right, then you've got the front porch and the sink, and all that junk comes from the VGA sync module. So the state machine consumes all that, and when it's time to draw pixels in the active display region, the state machine has to start emitting these pixel colors here for as many of the pixels that need to be rendered for the active display. Now, the VGA sync says, I want to be, let's say I'm in the upper left corner for in coordinate 0, 0. When I'm up here at column 0, row 0, I've got tile number 0 up there, okay? Now, when the VGA sync module is outputting the row and column number for this upper left pixel of this tile, remember it's 8 by 8 here, it expects, or it's doing so in the context of all the other signals that it's generating, like the border control signals and the sync signals and the vertical sync, horizontal sync, all that fun stuff, okay? But when we're running our state machine, when the VGA sync says, hey, render the upper left pixel of the first, tile number 0, I need to go find the color and the pattern and all the other fun stuff and figure out which pattern I need to put up there before I can render it. So what happens is, you'll see here is that the VGA sync module is generating the pixel clock, and its row and column will be 0 over here at T0. This logic takes 12 whole time periods before it can do what it needs to do that it should have done way over here if it was going to do it instantly and in sync with the VGA sync module output. But I can't, we can't do all this at once. So what I've got, you'll see in the state machine, is a pipeline. So among other things, I have to delay. We'll see some code that says, I'll take your vertical sync, your horizontal sync, the border, the active display, all those signals, and they will delay them by 12 VGA clock periods, and then output them from our state machine module. So that way, the VGA sync module can run without too much interference from the fact that it knows that it doesn't know, I should say, that the state machine's really not operating at the same time that on the pixels that the VGA sync module is outputting at any given time. It's always going to be 12 ticks later. All right. I want to point this out because we'll see it in the in the test bench waveform. You'll see these delay FIFOs in there. It's not a big deal. It's just, if this thing is going to generate the color pixels 12 time ticks after the VGA sync module wants them to be output, then we have to delay the other ones to go along with it, so that the sync and the borders and all that happen at this around where the color pixels are going to come out due to this delay. Okay, and we'll see that in the code as well. So again, I'm going to want to get the big picture stuff out so that when we look at the code, it makes sense. It's like, why is this? Why is that? Okay. So what else do we notice about this thing here? Well, each time we do this, I have 8 VDP time pixel units of time in here that are represented by 16 VGA pixel time units. So what happens is, every time we do 8 of these, what's going to happen is the state machine will go in, look up the name, look up the pattern, look up the color that goes along with the name, and then it will render those 8 pixels. Okay? And it'll do this starting, as I said before, 12 ticks after the VGA sync says, hey, do this one now, kind of thing. And you'll see that in order to look up the pattern, I have to have already looked up the name. And I just stuck some example numbers in here. These don't really mean anything, but they agree with what you see down here in this waveform down here, okay? So let's have a quick look at this. We already talked about how the video RAM works in the VDP in another video. So we know that the CPU can do this, you know, it's doing like read ahead logic and stuff for, in case the CPU wants to read, but the state machine also needs to be able to read from it. The state machine has to get what it wants when it wants it, or we can't render the screen. So there's this notion of jumping back and forth, and I kind of talked about that last time when we went over the VRAM stuff. This is this other control signal that reaches in and says, I want this, I want it right now. So in the very next tick, if DMA tick goes on, that's the state machine saying, I need to know the byte value at the address right here, and I expect to get it on the very next clock. Bam, okay? That's what this is doing. And as I talked about last time, I think I mentioned it anyway, that the CPU, the only way the CPU can read the VRAM memory is by using this like automatic counter thing that automatically advances after every time the CPU reads a value. And the VRAM logic has this look ahead thing that it can use to pre-read the next value in case the CPU comes back and wants to consume it, right? Well, the reason we care about that in here is that what we want to do is make sure that these unused portions, when we're not doing these DMA ticks, happen often enough so that if the CPU is reading from the VRAM real fast as it can, that there's always going to be a couple of these times, which you can see there's a lot of time in here, and most specifically that we don't hog access to the VRAM read data bus too long. And too long, I think, in terms of pixel clocks, it's on the order of 4 to 5 VGA pixel periods in a row. I think we can actually hog, if we wanted to continuously read in DMA mode, for 4 or 5 time periods before we've done it so long that the CPU might not be able to access 2 in a row if it's running as fast as it can, okay? I'm pulling that number out of my head. It's been a while since I've done the math. If you want to do the exact math, let me know in the comments below. We'll get there soon enough when we look at some other timing analysis and when we're doing the sprites, because the sprites do use the DMA addresses more often than this does. This never does even 2 in a row, so I don't even care. I know I can do multiple. I don't remember how many. Don't worry about it till we get to the sprites where it's, you know, doing a demand, you know, tons in a row of accessing the VRAM. We just need to make sure that no matter who's doing it, when and where, it doesn't happen so often that the CPU gets starved out. That's all I'm saying. Okay, in this scenario, it definitely doesn't happen because we never do more than 1 in a row here. Fine. So what do? We need to look up the name. Now remember this table over here. Look what happens. I got to look up 0 to 767 in the name table. What pattern do I want to show here? What pattern do I want to show here? What one do I want to show here? What one do I, and so on until we get down to here. All right. So which one of the number of the tile in here is determined by which one of the rows and columns we're rendering, which pixel row and column, right? This is 8 pixels high, 8 VDP pixels high, and because we're doing a 2-to-1 mapping from the VGA pixels, both horizontal and vertical, this is actually 16 VGA columns by 16 VGA rows. All right, so if you think about it, in order to render this one tile, I have to look up different rows from this pattern table over here 16 times for what I would call one row of tiles. All right, so we're going to see a counter that has to run kind of modulo 16 based on which one of the VGA rows we're rendering right now. Okay? And for each time we do this, and we go over this set of tiles this 16 times, we need to do the same tile numbers, the same name table lookups. You got to go 0, 1, 2, 3, 4, 5, 6, 7, blah, 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 up through 1F. And do it over and over and over and over 16 times. Once or twice for each one of the VDP pixel rows in here, okay? Then we move on to the next row of tiles and so on. So in the finite state machine, we're going to see some logic that does this weird counting. 0 to, when it gets up to 20 in hex, it goes back to 0 again, and it does it over and over until it gets up to a VGA row modulo 8, or actually modulo 16 in terms of VGA pixels, or 8 modulo 8 in terms of VDP ones, right? And then it'll start going through tile number 32 through whatever, you got a 63, okay? And so on as we go down this thing. So this is going to be repeating the tile numbers in order to get a different row of the patterns, so that we can get these all drawn. Then we move on to the next one and so on. So what are we doing here? We need to get the pattern, the name, out of the name table. And then we look up which one of the 8 bytes, because remember, there's 8 by 8 pixels in graphics mode 1. So the first VDP row of pixels comes from 1 byte in this pattern table, which is the byte that comes one before the byte in here for the second row and the third row and so on, because all 8 rows will be right next to each other in here. But again, we only render 1 row of this tile and the same row for the next tile and so on before we come back to the following row of tile 0 and that same following row of tile 1 and so on. So the way we access this, we're going to be jumping around a lot, because we can't just render all of this tile and then move on and render this one and so on. We do part of this, part of that, come back and so on, okay? So what does the math down here mean? It means that in order to get the pattern, we have to have already looked up the name. And that's also true about the color. The color depends on the name. The name depends on the, what they call the position, or I call the tile number. Which tile are we doing? So we need to make sure that we got what we need before we need it, is what I'm getting at. So the first thing we do is we look up in the name table and say, hey, I need the value for the given tile that I'm trying to render. The first one will be, 0. So it goes and grabs the value from that guy, and I'm just assuming, okay, that's pattern number 81, for example, here, okay? That I store in a thing called the name register to hold on to it for the duration of me needing it while rendering these pixels down here, okay? So now that I have the name, I can go back and look up the pattern and the color, because the address of the pattern depends on the name, value, M, and the base address of the pattern table. And then I go back in the memory again, and I go in there and get the base address for the color table, and the value M, the name, right? The pattern name, they call it, divided by 8, gives me the offset into the color table. So I have to calculate these things based on the values come out of there. So we got a chicken and egg. We need to make sure that we got this guy before we use it to get these other values. And it's not until I get the color value and store it into the color register down here, which I have to do after I get it from the memory, as you can see here, that I can then consume it and use it to render these colors. So what's going on here? I grab the name and I put in the name register. I then grab the pixel pattern and I put it into the pattern register, and you'll notice here it starts out with the 85 that I got here. Now, every time we move to the next pixel that we're going to render, look at this thing is changing. What is it doing? It's shifting it left 1. Because remember, when we render a pattern, it comes out of the pattern memory, and the most significant bit of the pattern byte, that bit is the first one that goes on the screen, and then the next bit, the next most significant one, is this following one until we get to the least significant bit. So what I'm going to do is I'm going to just simply shift it left one bit each VDP pixel when I'm rendering, okay? And the most significant bit in this pattern register will be latched at the end of each one of these phases into this pixel reg 1-bit register. So you can see the most significant bit here is on because it's an 85, so it gets latched in here and it's a 1. I made this red because we don't know what it is before we get here, because I'm only looking at this one character without any context of what has happened before and what we're really kind of going on to next over here, all right? But I do know that if this is 85, at the end of this period, I'm going to latch the most significant bit into this register here, which is a 1. And then I'm going to shift it to the left, which gives me 0A, because the 8 most significant bit will disappear. The 5 shifted left once becomes the A, and the most significant bit here is clearly a 0. And at the end of this one, I clock that one into the pixel reg and so on. So this is the on, off, on, off, on. This is a black and white stream of pixels. Or more, like they said, the foreground, background, foreground, background, foreground, color. This chooses which colors that we get from the color register that happen to arrive just in the nick of time, right here when I say, go calculate and grab the color value from the color table at the address that is calculated from the color base and the value of the name down here, the 81. So they combine together. Look it up, give me the value out of there. This thing gets latched into this register, and this register down here, based on whether this is a 1 or a 0, will be taken and sent out on the 4-bit output that comes out of the VDP. That tells me which color I'm supposed to have. Okay, it'll either be the most significant 4 bits of the color register value or the least significant 4 bits. That's all shown in the manual. We talked about all that long ago on my channel before. So these colors, you can see there's a color sub-0 1, color sub-0 0, and so on. These colors, the 1s and 0s match these 1s and 0s on this signal here, delayed by 1 VDP pixel time period. All right, so this is what we expect to see. This is how the state machine works. State machine has what I call 8 phases, and I implement them using a ring counter and a 1-hot case statement that uses the ring counter as the input to see which one of the phases that I'm in. All right, so these 8 phases represent the fetching of all the data that I need to get in order to store them in the color register and the pattern register that shifts so that I can continue to do the color codes over the course of time, even after this 8 periods have passed. Because remember, I can't render until time step 12 anyway into this set of 8 VDP pixel phases, okay? So this overlaps into what would be T12 of the next tile pattern row that's rendered afterwards, okay? So that's why this thing reaches out. Now, to circle back a little bit, where I was talking about the text mode and saying my text mode will just simply work because I'll just throw away what is these last 2 pixels over here. Well, what happens is that I will simply delete these 2 phases that don't interact with the VRAM and don't update any registers anyway. And what happens is the next set of would be 6 phases instead of 8, starts early, and it clobbers the color register and the pattern register and just starts the next one going right here, the next one being the next tile. That's why whether it runs 8 pixels wide or 6, it'll just work, because the logic down here is free running and doesn't care about what clock phase I'm really in. It only cares that there's data in the pattern register and the color register in order for it to render these 8 pixels. If you let it go too long, this thing would eventually become all zeros and it would just start rendering the background color and get seized up. But don't do that, okay? So just a little bit of insight is what we're going to see here. So let's see how we do this. Now, as I showed in my last video when we were talking about the VGA sync module, the best test case, the best test bench for the system as a whole, the VDP, I should say, as a whole, is the one for the entire Project Nouveau up in this directory here. So what we're going to do is, why don't I go ahead and fire this up now so we can have a reference to see what this thing is doing. I was just running this. Let's go ahead and clean it up. If you type make and we do the VDP 99, you do that to run, compile it all and run the test bench. You see a lot of debugging output. Takes a while. It's running an entire frame and then outputting all the lines of the data file. Let me get that in the background. Let's also scroll back up. I didn't know if I saw any warnings or something. Oh, this is all the timescale cruft. I've showed that on my channel before. Those are just warnings, not that concerned. That's because I have the timescale specified at the top level file and I didn't put them in the other ones. I should probably go back and do that. Blah, blah, blah. Let's open it up. Not enough words. This is because the RAM that I used to pre-populate the VRAM image, because I don't want to actually write all the code to fill up the VRAM with a bunch of CPU I/O cycles in the test bench in the simulation. I just dump it all in one fell swoop, and I only fill in part of it. So this ends early. And then there's a bunch of debugging stuff because I'm working on the sprite stuff. We're going to ignore the sprites for now. They are incomplete at best. And we only have so much time in any one of these videos anyway. Let's go back over to here, VDP 99. All right, so we want to see the state machine. We pretty much covered everything else, at least enough of it that you can piece together the big picture here. And this is the last part of the VDP anyway. So let's see what's going on in here. I talked a lot about the VRAM and how that all works in prior videos. In production, this is set to 12K. The default is 8. We calculate the number of bits we need in the memory bus automatically based on the amount of data, and that's going to dictate the number of wires that go over to the VRAM stuff. We talked about that on the VRAM side of this whole thing in a previous video. The data here come from the registers. Months ago, when I recorded the episode on how we CPU writes into all the configuration registers, okay? These are the results of that. All the configuration registers that can be written emit their various bits that are consumed in these diagrams here. And these bits, the number of bits that you see transported out of here match these. Like, for example, register 4 will only have 3 bits in it, which is going to be the upper 3 bits of the VDP, whatever the heck this thing is. Starting address of the pattern table should have 3 bits in it, right? So the pattern table base, for example, is here, and you see it has 3 bits, all right? Now, I did this because what I'm going to do is I'm going to implement the math shown down here in Appendix C. Somewhere in here in the manual, they have these simple little pictures that I didn't go far enough, I guess. There you go. Graphics mode 1. So what happens is, this is, for example, the pattern table base address, name table base, NTB, which has, in this case, 4 bits in it. It was the pattern table base. is the 3-bit jobby. All right, so you got these 3 bits here. And of course, they decided to name it different things, I don't know, from different parts of the manual, but you can see what's going on. The way we construct the address that we're going to send over to the VRAM is by combining groups of bits. And this math is what you'll see in the state machine when we're calculating the values that are represented by these times in here when it says I want to do a DMA operation. All right. So this is where you get that from, and you'll see the code matches this exactly. And that covers graphics mode 1. You do it like this. Graphics mode 2, you just do it a little bit differently. Okay, but the only difference between graphics mode 1 and graphics mode 2 is what addresses you use and how you calculate them based on these 2 tables. Everything else that the VDP logic does is the same after this part is done. Same with text mode. The only different thing about text mode, and we'll see that in the code, as I said a minute ago, text mode runs through the phase number, this one here that ends in when the ring counter gets to a 20. So we drop off these last 2 phases here, and you go from this one and you leap over to phase 1 of the next row of the next tile. All right, so these 3 guys here are what you're going to see in the state machine. And everything else should be somewhat intuitive, all right? I'll talk about the stuff that took me a few thoughts to get in here, and the rest of it will kind of fall into place, I think. The usual stuff. We got all the inputs and all the outputs that we need. Stuff comes over from the VGA sync module. Then these are the pipeline delayed signals that I alluded to earlier, namely that if I'm going to render a pixel 12 VGA pixel periods late, I have to regenerate the horizontal and vertical sync and all these other signals delayed by those 12 clock ticks as well, so everything happens relative to itself. The relationship maintains and it's correct. So what do we got here? I got an integer that we must use in some for loop or some logic somewhere. I use a ring counter 8 cycle thingy for mode 1 and 2, and I should also say, well, and 6 of the 8 for the text mode. I'm not sure what that's all about. Stale comment. My ring counter, I hold on to the name table address, the color register. These names here, I hope match the ones on here, or at least are close enough so you can make the one-to-one connection there. We got the read tick register and all that. This stuff reaches over to the VRAM module that we already talked about. The tile counter and the tile row. This is some special voodoo going on here. And this is the main thing that you want to, one of the main things you want to see at the higher level is what's going on with these. These are going to be the things that govern the logic that I was talking about when we saw the image of the screen. Where the heck is that thing? When I was talking about how we repeatedly show the same tile but a different row. Okay? Remember, we're going to render 8 VDP pixels by rendering 16 VGA rows in the vertical dimension here, and then 16 horizontal by doubling up the 8 VGA pixels horizontally as well. And what happens is, based on the VGA row, we have to convert that to the VDP row number within this tile that we're rendering so that we can continue to use the same pattern but a different row from the same pattern each time we come through here as we go down the various lines on the screen. And that logic you'll see is managed in these registers here. We'll take a look at that in the waveform in a minute. These things here are just some shift registers. The pipe length is going to be that's your 12 VGA pixels of delay. I'm going to just shift these things through here. I think this may be kind of a crummy way to do this. It might be better once the smoke is cleared to get the whole thing done and we look at cleaning up the code. There may be a better way to do this directly from the VGA module, because I think I'm just wasting an enormous amount of LUTs that we probably don't need to waste in all these shift registers in order to delay these signals. All right? But, you know, I'd love to hear your opinions in the comments below or on the Discord. There's an invite to the Discord in the description below this video on YouTube if you want to chat about it. Myself and others are over there that dabble with this stuff, and I'm sure we'd all like to hear about it because, you know, cleaning this up would be nice. You'll see what's going on in the waveform in a minute. What do we got? These are sprite things. We're going to ignore the sprites completely today, so none of this is relevant right now. Here is my 2 always block state machine that probably needs to be refactored, but it's all one big blob right now. And this is the reset. We do this. Notice the ring counter is initialized with a 1 in it. That's because the ring counter should never be all 0. No matter what, it should always have at least 1 bit set in it. And then here's the other half. This is a very standard pattern for me. Whenever you're not resetting, we just simply take the next value that comes from the combinational circuit below and clock it into the storage register of our state machine. Very simple, straightforward. Then what do we got here? We got this is an always block that manages all the pipelines. I decided to put this into its own always block independently of this one down here, which is the big, going to do the bulk of the work that manages all this in here. Because all this really does is it just shifts the thing left. Okay, that's all that's going on here. What's happening down here? VDP roast, but this is some more stuff for the sprites. I created some we'll talk about that when we go to the sprites. None of this matters right now. It's just junk. And then we get into the main always block here. Bird's eye view. What do we got going on in here? The usual setup with some special stuff here I'll talk about in a minute. We deal with our vertical sync to reset the logic when we start a new frame of video. Then we have this if statement here. I'll talk more about why that's there. This has to do with the doubling of the pixels. This is what causes us to draw 2 VGA pixels for every VDP pixel, and I'll talk why in a minute. But look at what's going on here. If that is on, we go in here and we do this. There's my one hot case statement in here, and it ends there. That's the whole ball game. We're going to be looking in that if statement for the rest of this video. Down here is a bunch of stuff for me to kind of stub in and prototype the sprites, which we're going to ignore today. That'll be another video, and I got to finish it anyway and debug it and all that. And this down here simply is going to set the output ports to the values that drive them. For all the delays, it's just going to be the output of the shift register. It looks like I shift in the values from the most significant bit and shift them out of the bottom bit down here, okay? And I just take the color out reg and send it out the output port. You've seen this in a lot of my code in the past. And the VM, yeah. So, all right. So the only thing we got to worry about now is this always block right here, okay? So let's see what's going on here. Let's take our waveform. Now, remember, this is an entire frame of video. So there's an awful lot going on in, oops, here. So what I'm going to do is I'm going to just put every single thing on the screen and then delete a lot of excess stuff. Because you remember how the style I use for my state machines, this is the state machine module down here, okay? In the test bench, and I think I showed you this last time, the test bench instantiates this unit under test, which is the VDP 99 in the Nouveau directory. That then creates the VDP 99, which is this, and in the VDP 99, which we've seen before, it creates a finite state machine, the register interface, the VRAM memory, and so on, okay? So this is the module that we're interested in right now. If I take all those signals and I say append, I'm going to get an enormous amount of stuff in here, okay? and I'm stammering around. You see the next and the reg, and a next and a reg, and all this stuff. Because in my state machines, the combinational circuits always output, here's the next value that I need to store into the reg on the leading edge of the next clock. And the clock that's used in this entire part of the system is the VGA pixel clock, which is going to be one of the fields in here. Let me make this all fit on the screen. I'm going to slide it over to the left so we get a little more real estate here. Here's my scroll bar. Somewhere in here there's a pixel clock. Right there. Okay, here's the reset. We don't really care so much. I'm going to put that up here. Oops, get it up there. Oh, for crying out loud. Hello. Just get this thing out of the way. All righty. Column last. A lot of this stuff comes from the VGA sync module. Border actor pipe reg. Let's first start with these pipe regs, then I'm going to delete them, okay? Let's look and see how that works. That's just a shift register. And if we look at this border active signal, where are the rest of the border active things? Where are my B's? Well, that's the only one. Horizontal sync. Row last, ring counter, blah, blah, blah. We can get rid of all the sprite junk. Sprite attribute table, sprite tick. None of this matters. Just delete all that. Cut it off the screen. There's my tile counter. And what do we got? The reg and the next. So what's going to happen is get rid of all these nexts. I'm looking for the rest of the border stuff. It'll be like vid border or something like that. Pipe, blah, blah, blah. Name, DMA, address, foreground color, the mode. We're in mode 0. Mode is set to 0, which is graphic mode 1, I believe. Name table base register, the pattern base. What is VDP SMAG? I don't remember what that is. Oh, that must be some sprite stuff. I suspect it is. I'm going to just delete it anyway. If we need it, we'll bring it back. VDP, that's the sprite size. Delete. Cut it out. Active. Active 0. These come from the VGA sync and the active out. Active pipe. And the okay. Here's a nice pipeline all in one group, and then we're going to delete the pipeline. We'll use the video active part to do this. Remember video active 0 and video active. Video active 0 is the signal that comes from VGA sync that gives me this signal 1 clock earlier. So this is useful for other reasons, but what I'm concerned with right now is the active and the active out and how we use this pipeline. So if we scroll out, you see that video active goes on down here. If I turn on the horizontal thingy, show wave highlight like this, right? So right in here, you see this thing go high. Just a little more detail on that. And we zoom in. Let's look at this. All right, so among other things, look what's going on here. When video active, let's not worry about video active 0. It just simply goes 1 clock early. If we scroll up, we'll see the pixel clock. That's the period of the pixel, a VGA pixel, okay? Now, video active here, when it goes from 0 to 1, I start shifting it in. You can see it happening here. There's an 8 and then a C and an E and an F. That's the 4 clock ticks shifting this bit in repeatedly until the least significant bit finally gets set right here. And in the next following clock, you can see this edge go high here. We got video active coming in from VGA sync, and this is it going out. Now, the whole point of this pipeline is to create this delay. All right, so I showed you the shift registers. There they are in action. If we delete all these rows, eventually we'll be able to fit everything on the screen, and that's my goal in clowning around with all this. We see the V-sync in and the V-sync out. They're going to be delayed, and here's the V-sync pipe junk. So where's vertical sync? It'll be all the way over here at the end of the thing. So you're going to see the same kind of a thing happening over there. You see the thing go in, you see the shift register filling up, and you see it coming out. So we don't need to see that. We understand this. We're geniuses. We don't need to see all that. So what I'm going to do is continue to delete all these things. So I'm going to just delete all these pipe registers and make ourselves some room. Then I'm going to go in here and I'm going to delete all these next signals. We've seen enough state machines to understand that the next signal, what they mean and how they work. We don't need all this noise on our screen. Pattern next in the reg, right? And you can see the scroll bar is getting a little bit more manageable here. Now, I'm going to leave these two on. So I'll leave some of these in pairs like this, the column last indicator, because we can get disoriented is the problem. Sometimes we're thinking about when the VGA sync is generating a signal, and other times we're thinking about when we're going to send it out to the screen. And there's going to be this delay here, and here's our pixel clock. So you'll see it, and 12 clocks later, it'll go out, okay? All right, I think we got enough of this stuff removed now that at least we can probably kind of get an eyeball at what's going on. So let's get over here to the beginning. What happens when we come out of reset, okay? So there's a reset signal that starts up our simulation. I showed the simulation source in the previous video, so I'm not going to go over that again. Here's the reset, and the reset goes off here. The first thing that the VDP is going to do is start drawing the border, because it's what it's going to do. As I said before, the 0, 0 is in the upper left corner of the screen from how we number the rows and columns. So the first thing it's going to do is start rendering in the upper left corner, which has got a pixel that's going to be the border on the very first row of the very first VGA row. And if you look down here, you see the pixel clock, you see the pixel column and the pixel row. So I'm on row 0, column 0 during this time. Then we go on to column 1 and 2 and so on. Now, what do we got? The border active out is delayed till it's over here because you got the clock, 12 clocks of delay. What's going on there? If we zoom out, where's our colors? There you go. Color out goes to 4 here. So it looks like it's gonna, what is it gonna do? It's gonna do a 0. It takes a little while to get itself going over here, I guess. It's gonna send some garbage out, I guess. And then it's gonna send the 4. And the reason it doesn't do a 4 there is because the registers aren't initialized yet in the simulation. So this starts up a little wonky in the simulation. So what happens is the background color register isn't set until here, and the base for the color table isn't set until here, and so on. And what I'm doing in the simulation is I'm actually generating register write operations into the VDP for a while it starts up. So when it's really going, timing-wise, it wants to render the upper left corner, but the VDP isn't configured until we're way over here. So I'll leave it as a test to the viewer to understand what's going on in the simulation when we come out of reset. The reality is, by the time you start the second frame, which is way over here, you can see a graceful beginning of a frame with everything set up correctly before the frame starts being rendered. And we're back to row 0, column 0, which is going to be over here somewhere after the vertical sync. There's the last row signal we talked about from the VGA sync. So here we are back to row 0, and column 0 will be like right over here somewhere. And now we can see it starting up more gracefully for the second frame, right? So there's the border active coming out of the VGA sync logic, which is also the thing that's generating the pixel column and row numbers, and they're all delayed by 12, and that's why this is over here. We come out of reset, or rather, come out of the vertical sync here, and the border active goes through there, and the color will be set to the border color at that time. Somewhere in here, there'll be a color register. Oh, what we need to do is look at this, which is the actual thing that holds the color register, the 8-bit value. Foreground is 4, and the background is a 6. So the background color, which is used for the border, is what we should see coming out of the color output register, and that's why we got a 6 in there. Okay, that's fine. Fine. So you see the border going, and then you see the border is small, and then you see a bunch of activity. This is the active display region, another border, and then you see the horizontal sync and border, active display, and so on. All right, so that's what you're seeing when we look at this whole thing. And this is one entire frame of video. So if we zoom in over here, while we're looking at the code, what do we know from a bird's eye view? Let's look at this. When we render a row, we're rendering one VGA row at a time. So we're going to do 2 of those before we move on to the next VDP row. So look what happens here. Here's one row in terms of time, because you can see the border, and then you see pixels going out, and then the right border, and then you get the horizontal sync. You see a border, active display, border. Now, you see this pattern here? It looks the same as this one over here, because it is, right? This is your 2 VGA rows rendering one VDP row, okay? And as we scroll to the right, you'll see these in pairs. This one and that one are exactly the same. These 2 are the same and different than the one over there, and that makes a certain amount of sense. These 2 here, these 2 are the next pair of rows. This one here and whatever comes after that will be the same. These 2 here are the same. These two, right? So we expect that. These 2 are clearly the same. And so on. As we go down the screen, you can see these based on the visual noise that's involved in these various things. We finally get to the bottom of the screen, somewhere over here. We're going row, row your boat, blah, 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 blah. Oh, the whole darn screen ends way over here. And then you see the vertical sync and so on way over there. There's a lot of rows going on in there. And there's a lot of them that are blank in the test data that we're using here. All right, so just so we realize, that we're getting what we expect out of this. This noise over here is the sprite logic running that we're going to ignore for now, because it reads the memory for the sprite table before it does a row. And the impact of that is you see a bunch of accesses on the video memory here, okay? But we're not that concerned about that right now. All right, so let's find a row that makes sense. Now I'm going to pick this row. Let's find a tile, the first row of a tile that makes sense to focus on. I submit that this one and that one are not the best choices. And the reason I don't want to choose this one is because the color 0, remember I'm looking at the color register. This is the color for the pattern that's being rendered in this first tile. And 0 means that it's transparent. And I wanted to make sure my code did the right thing. This is a little more advanced because what does it mean when I'm rendering a transparent pixel? And I want to talk about that. I'll leave that as something for later. This one here is 4 and 6. Well, it just so happens that 4 is the VDP background color from the configuration registers. And the VDP foreground color is, I think, 6. So the problem with that is it can cause you to misunderstand where these values come from. So if I choose 75, neither of these color codes are in use and could be confused with any other values from any other registers at this time. So the third tile is a pretty good example on what to start with. Now, if we zoom in, and we look at our ring counter is what we want to look at. Where's our ring counter? We got to get these lines arranged for maximum readability. Color out. Oops, when I was messing around, I broke this because what happens when you see this in this line, it means I moved this in a way that line doesn't line up where it's supposed to be. So I'm going to delete it. And color out reg and color reg are no, those are different things. When I'm moving things around, sometimes I break them. No, the color reg is an 8-bit value that is the foreground and background color in it, and this is the output color that should be sent to the DAC to render the current pixel. So these are two different things. Fine and dandy. So here's my 75. And here's my ring counter, 1, 2, 4, 8, 10, 20, 40, 80. So this period of time, I should go from here, and then I should put the white line right there. And delete the... this thing is off the screen. Okay, so this represents the 1, 2, 4, 8 that we saw in this here, the 1, 2, 4, 8, like that. So what we're going to see is we're going to see it fetching the name and the pattern and the color in a pattern that looks like that. If we can find the same signals, and we should see them down here. Here's the memory stuff going on, right? You'll see there's the read tick signal. We could probably put them kind of in the same order and make it match this if we want to. I strongly recommend doing that. But when you're moving them around, don't break it like I did this one up here. And you can, my point is, you can take this whole row and move it horizontally, which really is a screwy feature. You don't really want that. So where's my DMA address? Now, this matches this thing, so it should look a lot like that, and it does, because you see the 1 and then the other 2 over here. There's my ring counter here. It belongs up there. Okay, so at long last, and the 75 here is the color that's used in the tile that we want to look at. Remember that the colors are reused by many different name values, and when I initialized the VRAM, I set each one of the tiles to a number that I just count. So what happens is, if we look at the name register while it's fetching the names, the first one is going to be 0, and then you see a 1, 2, 3, 4, 5, 6, 7, 8, and so on. Well, what happens is, because I've done that, it will take the first 8 tiles, 0 through 7, all have the same color. And then the next 8 will have the same color. And it's not until we get to the third group of 8 that we end up with this particular color. So while this says 75 before it moves on to whatever the next color entry is from the color table, there's going to be 8 tiles rendered in here. So when this thing is on this color, the ring counter should cycle a bunch of times. So where is our ring counter? The ring counter is up here. The first one starts right there. And what do we got going on here? So when this ring counter is a 1, we're dealing with this time right here. Okay. So we see it. What's it doing? It doesn't do anything until we get over to the second phase. The ring counter is equal to 2. When you see that there's a read tick and use an address over here saying, hey, I want to read something from address 810. This is what you get when you apply the Appendix C math and do this when you grab the pattern base plus the name number, which is going to be 10 in hex, plus these things here are the 3 bits for which one of the VDP row numbers we're on, and we'll see that math in a minute. So you're going to see the fetch, and then you see the other 2 fetches in here, and you see the thing propagate through down our pipeline like we saw it on the summary diagram that we opened up with. Okay, so now that that kind of matches what we're used to seeing, let's look and see what happens in the code here. What do we got here? I set this to 0 unless I override it below. This thing here means that, you'll notice I normally just say, hey, set the next one to the current register value. So leave it alone unless I change it is the philosophy I use for all these variables down here. But when it comes to the DMA stuff, I say, unless somebody specifically says, I want to turn on the read tick signal for the DMA access, and I give it an address, just set it to this. And this comment will make more sense when we look at the at the case statement in a minute. The bottom line is that by making sure it's always 0, if I make a mistake down here while I'm debugging, I don't end up in a situation where I turn it on and leave it on and make it hard for me to debug. There's also the fact that we'll see the state machine doesn't trigger every pixel. It only does it every other pixel. So it makes it difficult to shut this off and allow me to make it only one VGA clock period long. All right, this code will turn it on, and then the next time the pixel clock, the VGA pixel clock runs, it'll fall through this logic here, and it'll shut it back off again. That way, it only stays on, as we'll see, for only one a period of the clock. So what do we got going on down here? We handle a vertical sync. Remember, this is the combinational logic for the state machine. Anytime the VGA sync says, hey, I should be doing vsync now, what I need to do is I need to move the tile counter back to the upper left corner, which is going to be 0. Now, let's see what this gets used for down here in a second here. This has to do with the fact that I got to keep re-rendering the same row number over and over again because I need to render it 16 VGA rows, use the same tile number before we move on to the next one, all right? So I have the notion of which tile am I on and which tile number was at the beginning of the current row, which is managed down here, so that I can use this when I reset myself back to the beginning of a row and start over again and use the same tile many times until I count modulo 16 to the next row where I have a new set of tiles. All right, so think this through for a second here. I added this note just now to make sure I hit it. All right? The column last out signal comes from the VGA sync. It says, I'm doing the last column. And you'll see below, during phase 6, this could cause a problem. But I point out in here, and this happens a lot in here, this code takes a lot of advantage of everything else being done in a way that we can assume gives us the ability to simplify our logic in here. So I warn you, if you start playing around with this, the whole house of cards can come down if things like we assume that these things always end when pixel column is odd or even and stuff like that. Okay, so if you start changing the timing on this, the whole thing could blow up in your face. So be very careful of that. So this note here makes the observation that the last column out bit from VGA sync will only be true. It actually is true during, like, you know, the at the end of the back porch or something like that. It doesn't happen when we're in the active video portion of the screen, and we'll see why that's relevant down here. So we can, during that time, play around with our tile counters, is my point, because no one is using them during this time. All right, that's what your takeaway is on that. So what does this thing do? It says if the current row is not a multiple of 16, when the current row is a multiple 16, what we do is we move on to the following tile row. We want to use the same tile 16 times until we get on to the next tile row, and so on. So these two variables are used together. When it is not a multiple of 16, I got to start over with the same tile number. So what that refers to, so again, that refers to this notion up here, where every time we render this row, we need to do 8 VDP pixels before we move on to the next tile row, which is 16 VGA pixels before we move on to the next tile row. Now, each time we go across this row, I go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 31. 0 to 31, 0 to 31, 0 to 31, over and over and over again. Then I go 32 to whatever, okay? And I do that 16 times, and so on. This is the logic that does that. if I'm not a multiple of 16, I got to keep reusing the same tile sequence that I used last time. And I store that in this tile counter row reg. How does it get there? It gets there down here. When it is a multiple of 16, I do this down here. And what I do is I remember the current value of the tile number, because what happens is when I'm in a multiple of 16, it means I've just finished this guy over here, and it has a 31 in it, or actually at that time, it will have moved on to 32, because it will advance itself while it's doing the horizontal sync over here. And that 32 is what you'll see gets loaded into this thing. So it says the next time I come around, make sure that the tile counter row next thingy that I'm going to store for the next 16 times I do this is the one time I actually move that forward. All right, I'll leave it as a test the viewer to look closer in the waveform diagram to see how that works. It took me a minute or two to come up with this style, and again, there's some caveats in here. This only works if the top border is a multiple of 8, and you need to make sure that what do we got? That call last out is only true on like an odd numbered pixel or something like that. Well, we'll never do this. Blah 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 blah. What's going on over here? VSync. When I'm not in VSync, I'm doing this down here. Call last out is okay, but we use it again. We use call last. Here's the one that has to only occur on odd numbered pixels and stuff like that. Read all these comments, all right, if you're going to play with this. So this is how I remember how I'm going to reuse the same tile numbers over and over again as I move down the pixel rows. And down here is what I do on each pixel row, okay? So by asking if I'm in an odd numbered column, it's the only time I'm going to execute the logic down here in my state machine. Otherwise, I'm going to leave the state alone. So what that means is I'm dealing with this second thingy here in each one of these ring counter phases. So look at this. I'm at T0. This is an even numbered column. If you watch the pixel column here, we can zoom in on that in the waveform. This is going to be an even pixel column. That's going to odd, even, odd, and so on. And what that's doing here is it's telling me that the state machine logic here will only change the next state when I'm on this right-hand side of each one of these phases. And that is what we'll see is during phase 1, we'll see it say, calculate the DMA address in the tick register for the next phase over here. We'll set the DMA tick next and the VMA DMA adder next values in the state machine here, so that on the next leading edge on the even numbered VGA pixel number of the next phase is when this will take place. Okay, and because you saw above, I always by default turn this DMA tick off and DMA adder off no matter what, regardless of whether I'm in an even or odd pixel, unless I overwrite it down here, which you're going to see me do. That's why this is only 1 wide, while all these other ones are going to be 2. Okay, there's even odd jazz going on. When you look closely, you're going to want to keep that in mind. That's what this is doing. And what do we got? If I'm on the very last column of any given row, and I need to make sure that happens on an odd pixel column. Otherwise, remember, this only runs when I'm on an odd column. So I need to make sure that I don't change my VSync timing so that becomes true on an even column. Otherwise, it's going to get messed up. So what am I doing here? If I'm on the very end, I want to reset my ring counter. And if I'm not on the very end, I'm going to just shift the ring counter to the left, and this is going to free run. This probably, I don't know, this might be getting stale because I've rewritten the code a couple of times, but this is the thing that makes sure that the ring counter always starts with a 1 for the row, even if it ends in a weird way, or during the sync period it gets out of whack, which could happen. In my mind, when I first wrote this, we have to be always concerned about what happens if we're in text mode and we really don't have 8, 8, 8, 8 for each one of the numbers of columns of the VDP tiles. Some of them, they're going to be 6s in that mode. So this kind of just slams it on. It says, if I'm on the last column, the next pixel represents the first column of the next frame, and that's always going to be synchronized to set the ring counter up to 1. Okay, pattern next. Now here's the logic that always shifts our pattern register left. This thing here that's always moving left all the time, no matter what. But remember, it only does it on these odd numbered pixels, which is why it stays here for 2. And then on this odd numbered cycle, it shifts it left, and then it sits there until the next odd one, and so on. That's what this is doing. Pixel next is going to be the value, the most significant bit out of the pattern register. And because I do this separately, rather than simply taking the current pattern register's most significant bit and then using that as the pixel value, all right, this causes it to be delayed by 1 clock cycle, which is why when you see the 85 here and you see the most significant bit on here, it's not until this next time phase that you see the pixel reg go true. And I needed to delay that by 1 because the color is not ready until way over here. Okay, and then that is used to determine the color value that I get from color register, whether I'm using the most significant nibble or the least significant nibble, depending on whether this is a 1 or a 0. So that happens most likely next. Color out is the value of the left or the right nibble, depending on the current pixel reg. Okay, and if it's ever set to 0, that's the transparent color. And we don't have any way of getting, an external video input. So what does it mean to be transparent when I don't have anything to put behind it? So I don't know if I read this in a manual somewhere or got, rumor or whatever. I decided to just use the VDP background color, which is the text background, and the border color, right? I'm going to just send that out. If you say transparent and there's nothing behind it, I can do that. You could also hard code that to black or something. I don't know why I did this, but that's why that's happening. And that's why I said I want to be careful in my test case and not use a pattern or a color that has 0 in it, which is what you have over there. Because if you look in here, you'll see the background color show up as the output rather than a 0 and a 7, okay? So that's why that's why I decided to use one over here that has a color that's a 7 and a 5, okay? To make sure that this doesn't confuse everybody. Now what do we do? If the video is active, I'm going to play around with all the ring counter and I'm going to decide what to do. So in other words, this stuff only takes place in an active part of the display. The ring counter runs all the time anyway, but we're not going to go out and mess around and interact with the memory unless we need to, okay? So it only happens during an active part of the screen. And remember, this whole chunk of code only runs for odd number VGA pixels. This is a parallel case, full case. That means it's a 1 hot. I say case 1, and only one of these is going to match that. Only one bit in our ring counter is ever set to a 1, and all the rest are 0s. Okay, so here's a good example of how to use a 1 hot case statement. Now, I added these comments in here because, you go through here and you're like, oh, what's going on during the, the first phase? This is phase 1. By that, I mean it's the O1 here, which is the least significant bit of this counter reg is true. What am I supposed to do? Well, remember this only gets executed for the odd VGA pixels. Then and only then do I set the DMA adder next to the base, followed by the tile counter register. This math is the stuff that comes from Appendix C over here. That's why I wanted to point this out. All right, so what am I doing? And I'm in phase 1. What am I doing? I want to get this out here. That's the name address for the name table, which is the math right here. That's the pattern, color, and the name. So you got the base address plus the row and the column. Now it turns out that row and column is really just the tile number. So I'm going to use my tile number for this. Now when you're in text mode, normally it would be a little bit different, but if you do it this way, it comes out okay in both cases, because if you go down here and look at text mode, it says text position. And they say this because it's row times 40 plus these are not powers of 2. The math doesn't work out very well. The bottom line is in both cases, it's just simply the tile number, starting from 0 in the upper left corner down to whatever it is in the lower right. So if you do that math, this always works, okay? And we set the read ticks next to 1. By default, it would be 0, which is why the next clock period, you see it go high. You will see it go high once, then you'll see the address go out. In the following clock cycle, which is going to be an odd number pixel, you see the VRAM come back, and I can then latch it at that time into the name register. So that's what, these are pretty simple little states, okay? And this is, this style of design is not what a lot of people like. This is kind of messy. It's just started filling up with code. I apologize. A lot of people usually create a state machine that runs the next state logic in one always block and then puts all this stuff in another always block based on the current state. And, mine grew into this style, which is a little bit different. Could be a little messy, but there's not a lot going on in each of these states, so this works out, in my opinion, okay. Again, I'd love to hear opinions on this in the comments below if you think it's terrible or use this technique, that one, whatever. Right now, I'm going for something that works and passes the timing closure. So what happens in the next phase, right? So if it's the second phase, then this bit will be set. What I want to do, I want to capture the tile name from the pattern table. Well, that's me grabbing this value and storing it into the name reg here, okay? So what am I going to do? I'm going to take the value from the VRAM that's currently must be the value from this address up here and store it into the name register on the next leading edge. That's all I got to do in that particular time slot, because the time slot 4, I don't do anything in over here. This third one, there's nothing to set up. But during time 4 on the odd numbered pixel, I need to set up this stuff over here. So we need to prepare the address to fetch a tile pattern, right? So while we don't do anything, we're capturing, arguably, we capture this at the end of this second one here, and we don't set up anything until the right side of 4. We don't capture anything, I should say, during 4. We wait until we get over to this guy over there. So this one's this one. All I'm doing here is I'm saying issue an address so that I can grab something in the following phase down here. Now we get to the point where I'm like, well, am I in graphic mode 1, or am I in graphics mode 2, or am I in text mode? I didn't implement multicolor mode because the manual said that it's only supported by some different chips, and it seems low-res wonky thing. I don't know. If you want to see it, we can probably add that code in here. So as I said earlier, the only difference between these modes is how you calculate the address. Is it going to be the pattern base followed by the name and the row number? Notice I leave the least significant bit off of this because I want the VDP row number, which is expressed this way. We ignore the least significant bit because the full pix row value would be the VGA row number. So I want this thing modulo 8 in the context of the VDP row. Pause the video if you have to and work the math out. You'll see this is probably what we want to do. Now when we're in graphics mode 2, I do it like that because in graphics mode 2 it says, I don't know what the XX is over here. Yeah, blah, 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 blah. MSB from the vertical counter. all 8 bits of the name, and then the pattern byte line number. That's going to be the VDP row number. I like the way they explain it differently in these two cases. I believe those are the same thing, which it is, because it's row 3 to 1 as is this. But you can see I got the tile counter and the name in here. Combined, that's these 2 bits here. And the name in its entirety goes here, and the 3 bits again from that guy down there. So that's why this math is the way it is. It is a single bit base address. It's either going to be 0 or 1 or whatever it is. There's only 2 places for the pattern table to be when I'm in mode 2. And then when I'm in text mode, the math works like this. So we go to find the text mode. What does it say to do? It says the table base name in the 3 bits like that. Table base, the name in the 3 bits like this. Okay, so these do directly match the doc if you know what to look at and you know how the names match. By default, what do? I don't read anything at all. If I'm in multicolor mode, I don't, I don't support it, so I'm going to just shut it off and say, I'm not going to get anything. It'll probably be black or something. I don't know. Your mileage may vary if you use a mode that's not supported. So what do we do then in the next one? All right, so I think you kind of got to figure it out here. What do we do there? We just grabbed the pattern, which is this. So then in the next time cycle, we're dealing with the odd side of this guy. We want to capture the tile pattern and prepare the DMA address for the color. Okay, so take the DRAM out and grab the pattern value. We're dealing with the fact that there's the pattern, and we're going to capture it at the end of this cycle, and we're preparing, that's what we're doing, to do a DMA tick with the color address now. And you'll see the same kind of a thing here. Depending on the mode, I calculate the address of the color table using a different style, give it in these thingies. So the color table is the base with a 0 and the name, or it's the, what is this thing? The color table base. And then I've got some vertical counter and so on. So there's 3 different ways to do it. You just do it the way they give you these tables. Actually, this one doesn't have a color because it is a global thing. It turns out when we're in the text mode, I use the value from the foreground background register, as the doc says. But if I'm in graphics mode 1 or 2, I use the math according to the formulas we just saw, and I don't support multicolor mode. The next phase we got here is when that bit is set, and that's the wrong diagram. So when 4 is set, that's the 1 0. So now I'm over here, and I'm going to want to capture the color, and I want to prepare the pixel reg and all that fun. Actually, that happens at the top of the loop. We already saw that. So here's where we differentiate between the graphics and the text modes. You say if I'm in a text mode, I just hard code it to the foreground and background color that came from the configuration registers that are up in the module ports from the register values that we talked about long ago. Now, the color next, otherwise, the color register value for the foreground and background will be the thing that came from the VRAM that came from the address that we set up here, okay? So that's what that's going to do. Then we get on to number 5, and this is the interesting thing about whether or not I'm in text mode, where we end early and stuff like that. So now we're over in this guy over here, and there's not much to do over here other than waste time until we get to the beginning of our the next 8 VDP pixels in these 3 states. So you don't see much going on. So what we do in this one is we ask, are we in text mode? If we're in text mode, then what happens is I'm going to just slam the ring counter to go back to 1 right now. And I'm going to set the tile counter, and I'm going to advance that at the end of this phase here, okay? That's going to effectively throw away these last 2 here, all right? That's why we're going by 6s when we're in text mode, or we're going to run all the way to 8 in the graphics mode. So if this doesn't happen and I'm not in that mode, I don't do anything at all. And I fall into here and I don't do anything at all. And then I fall down here. And then down here is when I finally advance myself to the next tile, which is the next, character tile on the current row. And then I simply fall through and wait for the next clock to update my state again. That's the whole thing. So, back to our 75. Let's zoom way in to make sure this thing is doing what we think it is. So this should be like tile number 24. So the VGA column, which would include the left border and all, and it's counting twice as fast as the VDP pixel counter would be, right? So this in hex, I don't know if that's the right value. I'm sure it is because I've run this and it does work. It comes out right. You can actually count them at a higher level and just count these out to make sure we got the right number. There's going to be 16 of these and 16 of those. And what did I say? 24. There'd be 32, right? And then the double the pixel numbers for the VGA ones. So this color, of course, was fetched as part of this cycle here, which starts right there. So now we should see. Let's go ahead and see if we can make sense of all this stuff. One full cycle of the 1, 2, 4, 8, 10, 20, 40, 80, and then that actually ends up over here. So what do we got? Here's some, what is this? There's the pixel register going 0, 1, and 0 and stuff like that. Looks like maybe we have a single pixel that lights up for this particular row of that tile. So let's watch what happens, right? So what should we do? We got to get the name. We get the name number, then we fetch the pattern and the color. So when we get this pattern here, the second time we see the data come from the DRAM out is when we get our pattern and these bits. And hopefully we'll see there's a single bit on in this section here when we fetch that. So here's the first one. The second one comes in. I got a 1C here. Well, that has more than one pixel set. Why would that? It's because it doesn't end here. This is the 8 phases of getting the data, but the data is rendered starting here, remember, starting with the phase that starts with a 1, 0 through the next 1, 0, which is way over here. So here's the other bits that are represented by the C in the 1C. Right, so the colors will render until we get over to, what is it, 40 over there? Starting 40 and here, and it goes until we get to the 4.0 in the ring counter value. So it should start rendering. Mine actually starts rendering. I shall put a tick right here for the 1C. So there should be, this should be this thingy like that, okay? So what do we got? We got a 1C, and then we got a 75 for the color, which is why the color turns 75 here. 1C goes into the pixel register there, and a 1C in binary is 3 zeros and a 1, and a C is an 8 and a 4, so that's going to be 0001 and then 1 1 and 2 zeros. So we should see 3 VDPs pixels starting here that are the background color, followed by 3 that are the foreground color. And that's roughly what we're looking at right there in terms of the pixel reg. So what do we got? We got a 75. So the background is 5. The foreground is a 7. So what we should see is while we've got these zeros going are the backgrounds. Should see some 5s, and then we see some 7s, and that is the color out reg right there. We do see 5s, and then we see the 7s here. And this is skewed by 1 clock from this pixel. So it's off, there's the background, and then we render it out. So that all works, and then you got your 3 pixels that are supposed to be 7. And remember, there's going to be 6 VGA pixels. 1, 2, 3, 4, 5, 6, before it then goes on to the 5 for our foreground, or rather the background color again, right? So it's the background is 5, and then we get the 7 and another 5. So this is doing the right thing in the right order, and it matches what we expect out of here. And if you go look at the VRAM initialization data, which is sitting in the directory over here, which is this right there, you can actually see this stuff up here is the pattern table. Notice the pattern for name 0 is all zeros. Okay, that might be a space character or something like that, and so on. And we got a bunch of different patterns in here. I don't know what these are. These might be actual. This might be the real data that has a whole alphabet or something in there. This then is the name table data, and this is all accounts for all the bytes that go into the VRAM, and I configured the configuration registers so that these tables start where at these various offsets or where the bytes appear in this initialization data file. So if you look at the name numbers, the pattern numbers, right, for each one of the positions on the screen, you'll see they start and they count 0, 1, 2, 3, 4, 5, yada, 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 and they count up until you get to here, and then they, I don't know, do crazy things. But if you then watch what happens for the numbers of the tiles that come out of there, those would be like the name addresses, right? Look at what's happening on this thing as it goes. You get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, yada, yada, yada. So these are the names that come out of that table. When I want to grab the tile number 0 in the upper left corner, I get the name of that is the same as the tile number, which is also 0. It can be slightly misleading if you don't realize what's going on, but I numbered these with their positions so I can make it, I can recognize it in the debugging output if I get the right values. Down here, this is the color table. And remember, the color table has names 0 through 7 are this color. Names, 8 through 15 is this. And names 16 through whatever that 24 or 23 are this. Okay, this is why you see an 07, a 46, and a 75, because here's your 07, 46, 75 here, because I made all the names match the address of their tile. So when you get 0 is 0 and 1 is 1, and you can see all these match up in here, right? So it's when you get to 8 here, you see the color change. And when you get to 10 in hex, you see the color change again. So again, this gives you the bearings of where all the stuff comes from and why it is the way it is. This stuff down here is filler and some sprite stuff down here that we'll talk about when we talk about sprites. I think this video has gone on way too long, and I think you got the hang of it. I hope you got the hang of it. You know how to connect the state machine to these thingies in here, and that's really all that's going on. It took 99% perspiration to figure out how to lay all this stuff out, but in the end, all you need to do is apply these at the right times, which are defined by these ring counter phases in here. All right, this is a pretty long video. I think we're going to stop here. I hope I covered enough of the basis for everybody to understand how the graphics modes and the text modes work with the tiles and all that stuff. Next time we'll play around a little bit more with the sprites. Got any questions, jump on the Discord. There'll be an invite link in the description below this video on YouTube. So, again, thanks for watching. I hope you're having fun. See you next time.